For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@eduassignmenthelp.com or reach us at https://eduassignmenthelp.com. Problem 3.1 Invariance of coding gain. Show that in the power-limited regime the nominal coding gain gamma C, A, of 5.9, the UBE, 5.10, of PB, E, and the effective coding gain F, A, are invariant to scaling, orthogonal transformations and Cartesian products. In the power-limited regime, the nominal coding gain is defined as scaling A by alpha 0 multiplies both dmin A and EB A by alpha 2, and therefore leaves gamma C, A, unchanged. Orthogonal transformations of A do not change either dmin A or EB A. As we have seen in problem 2.1, taking Cartesian products also does not change either 2-minute A or EB A. Therefore gamma C, A, is invariant under all these operations. The UBE of PB, E, involves gamma C, A, and KB, A, equals Cmin, A, / log A. Cmin, A, is also obviously unchanged under scaling or orthogonal transformations. Problem 2.1 showed that Cmin, A, increases by a factor of K under a K-fold Cartesian product, but so does log A, so KB, A, is also unchanged under Cartesian products. The effective coding gain is a function of the UBE of PB, E, and therefore it is invariant also. eduassignmenthelp.com. B. Show that in the bandwidth-limited regime the nominal coding gain gamma C, A, of 5.14, the UBE, 5.15, of PS, E, and the effective coding gain F, A, are invariant to scaling, orthogonal transformations and Cartesian products. In the bandwidth-limited regime, the nominal coding gain is defined as scaling A by alpha 0 multiplies both dmin A and ES A by alpha 2 and does not change rho A, and therefore leaves gamma C, A, unchanged. Orthogonal transformations of A do not change 2-minute A, EB, A, or rho A. As we have seen in problem 2.1, taking Cartesian products also does not change D 2-minute A, EB, A, or rho A. Therefore gamma C, A, is invariant under all these operations. The UBE of PS, E, involves gamma C, A, and KS, A, sadface 2/n, Cmin, A. Cmin, A, is also obviously unchanged under scaling or orthogonal transformations. Problem 2.1 showed that min, A, increases by a factor of K under a K-fold Cartesian product, but so does N, so KS, A, is also unchanged under Cartesian products. The effective coding gain is a function of the UBE of PS, E, and therefore it is invariant also. eduassignmenthelp.com. Problem 3.2 Orthogonal signal sets. An orthogonal signal set is a set A equals AJ, 1 less than or equal to J less than or equal to M, of M orthogonal vectors in Rm with equal energy E, A, i.e., AJ equals E, A, delta JJ, Kronecker delta. A. Compute the nominal spectral efficiency ρ of A in bits per 2 dimensions. Compute the average energy EB per information bit. The rate of A is log 2m bits per m dimensions, so the nominal spectral efficiency is ρ sadface 2/m, log 2m bits per 2 dimensions. The average energy per symbol is E, A, so the average energy per bit is B. Compute the minimum squared distance d 2-minute A. Show that every signal has k-min, A, equals m-1 nearest neighbors. The squared distance between any two distinct vectors is aj minus aj2 equals aj2 minus 2aj, aj plus aj2 equals e, a minus 0 plus e, a equals 2e, a. eduassignmenthelp.com. So D2 minute A equals 2E A, and every vector has all other vectors as nearest neighbors, so Cmin A equals m minus 1. C. Let the noise variance be sigma 2 equals n0/2 per dimension. Show that the probability of error of an optimum detector is bounded by the UBE/PR E less than or equal to m minus 1 Q E A/n0. The pairwise error probability between any two distinct vectors is PR AJ equals Q AJ minus AJ 2/4 sigma 2 equals Q 2E A/2n0 equals Q E A/n0. By the union bound, for any AJA. So the average PRE also satisfies this upper bound. D. Let m infinity with E be held constant. Using an asymptotically accurate upper bound square root for the Q function, see appendix, show that PRE 0 provided that EB/n02 ln2, 1.42 dB. How close is this to the ultimate Shannon limit on EB/n0? What is the nominal spectral efficiency ρ in the limit? eduassignmenthelp.com. By the Chernoff bound of the appendix, Q, x2, less than or equal to E minus x2/2. Therefore PRE, less than or equal to, m minus 1, E minus E, A/2n0 E, ln m, E minus EB log 2m/2n0. Since ln m sad face log 2m, ln 2, as m infinity this bound goes to 0 provided that EB/2n0 ln 2, or equivalently EB/n02 ln 2, 1.42 dB. The ultimate Shannon limit on EB/n0 is EB/n0 ln 2, minus 1.59 dB, so this shows that we can get to within 3 dB of the ultimate Shannon limit with orthogonal signaling. It was shown in 6.450 that orthogonal signaling can actually achieve PRE 0 for any EB/n0 ln 2, the ultimate Shannon limit. Unfortunately, the nominal spectral efficiency ρ sad face 2 log 2m/m goes to 0 as m infinity problem 3.3, simplex signal sets, let A be an orthogonal signal set as above. A. Denote the mean of A by m A. Show that m A equals 0 and compute m A 2. By definition, eduassignmenthelp.com. Therefore, using orthogonality, we have: by the strict non-negativity of the Euclidean norm, m A 2 equals 0. The zero mean set A equals A minus m A, as in exercise 2, is called a simplex signal SET. It is universally believed to be the optimum set of M signals in AWGN in the absence of bandwidth constraints, except at ridiculously low SNRs. B. For M equals 2, 3, 4, sketch A and A. For M equals 2, 3, 4, A consists of M orthogonal vectors in M space, hard to sketch for M equals 4. For M equals 2, A consists of two antipodal signals in a one-dimensional subspace of 2 space. For M equals 3, A consists of 3 vertices of an equilateral triangle in a 2-dimensional subspace of 3 space. And for M equals 4, A consists of 4 vertices of a regular tetrahedron in a 3-dimensional subspace of 4 space. C. Show that all signals in A have the same energy E, A. Compute E, A. Compute the inner products AJ, AJ for all AJ, AJA. eduassignmenthelp.com. The inner product of M, A, with any AJ is. The energy of AJ equals AJ minus M, A, is therefore. For J equals J, the inner product AJ, AJ is. In other words, the inner product is equal to M minus 1E, A, if J equals J and minus 1E, A, for J equals J. D, optional. Show that for ridiculously low SNR, a signal set consisting of m-20 signals and 2 antipodal signals, plus or minus A, has a lower PRE than a simplex signal set. Hint, CM